Listed spacing for a heat detector is the maximum spacing established during testing, showing how far apart detectors can be placed on a smooth, low ceiling. There are two methods for applying listed spacing: the square layout and the circular layout. In square layout method, detectors are placed in a square grid pattern. The distance between detectors is equal to the listed spacing. Each detector covers a square area. For example, with 50 feet spacing, 50 feet times 50 feet equals 2,500 square feet. In the circular method, every point on the ceiling shall be within 0.7 times listed spacing from a detector. For example, a 50 feet listed spacing detector radius is 0.7 times 50 equals 50 feet. Depending on the architecture, square layout suits grid-like spaces and may require fewer detectors, while circular layout is ideal for irregular areas and corridors, often maximizing coverage with fewer devices. As you can see in this irregular space example, the circular area method reduces the number of detectors. With the circular method, only 5 detectors are needed, while the square method requires 7 detectors to properly cover the area. Heat detectors are typically spaced according to standards established through full-scale fire tests conducted by underwriters' laboratories. These tests determine the listed spacing, the maximum allowable distance between detectors under ideal conditions. The UL test installs standard automatic sprinkler heads 10 feet by 10 feet, spacing around the alcohol pan. The heat detectors are placed around the automatic sprinkler head's fuses, becomes the listed spacing of the heat detector. Real-world environments often present challenges that affect heat detection performance. High ceilings, structural elements like beams and joists can interfere with heat movement and delay detector activation. To address these variables, NFPA 72 requires that actual installed spacing be less than the listed spacing when such conditions are present. Listed spacing is established by the manufacturer and reflects the detector's ability to reliably respond to thermal conditions across a defined coverage area. UL 521 evaluates the detector's sensitivity, response time, and operational reliability under controlled fire scenarios. The adjusted spacing is referred to as the design spacing, or SD. If no environmental adjustments are necessary, design spacing equals listed spacing. But when conditions vary, NFPA 72 provides specific formulas and reference tables to calculate the appropriate reduced spacing. When designing heat detector layout in accordance with NFPA 72, determining the correct spacing is critical to ensure code compliance. This process involves 3 steps. It starts with the listed spacing. Step 2 is to apply the ceiling height reduction factor. As ceiling height increases, more ambient air is entrained into the plume, making it cooler. The higher the ceiling, the smaller the allowable distance between detectors. Step 3 is to apply surface adjustment factor. Architectural features like beams and joists can obstruct heat flow. After applying both the ceiling height and surface adjustment factors, we arrive at the final value known as design spacing SD. Design spacing is always less than or equal to the listed spacing, ensuring that system is working properly on the real-world conditions. When designing heat detection systems, ceiling height plays a critical role in determining detector spacing. As a fire plume rises, it entrains surrounding ambient air. This process cools the gases and dilutes the concentration of fire products, making it harder for heat detectors to respond quickly. To calculate this adjustment, we refer to Table 176351 in NFPA 72. This table provides reduction factors that must be applied to the manufacturer's listed spacing. For example, let's say a heat detector has a listed spacing of 50 feet. At a ceiling height of 20 feet, Table 176351 specifies a reduction factor of 0.64, so the adjusted spacing becomes SD equals 0.64 times 50, which is 32 feet. In addition to spacing reductions for high ceilings and complex surfaces, code also defines a lower boundary for how closely heat detectors should be placed. The minimum spacing of heat detectors shall not be required to be less than 0.4 times the height of the ceiling. The type of ceiling construction plays a critical role in how combustion products move and how effectively heat detectors respond. NFPA 72 classifies ceilings into three main categories: smooth ceiling, beam construction, and solid joist construction. Joists slow down the ceiling jet, the horizontal movement of hot gases, especially in the direction perpendicular to the joists. To compensate for this, the code mandates a reduction in spacing. The listed spacing perpendicular to the joists must be reduced by 50%. This ensures detectors are close enough to respond effectively despite the slowed heat movement. No spacing reduction parallel to the joists is required, since heat can flow more freely along the joist channels. As per NFPA 72, Section 17.6.322, under joisted ceilings, heat detectors should be mounted at the bottom of the joists. When beams project over 4 inches and are spaced more than 3 feet apart, they block the ceiling jet. Code requires detector spacing perpendicular to the beams be reduced to 2/3 of the listed spacing, while spacing parallel to beams remains unchanged. When ceiling beams are very deep and spaced far apart, heat movement is significantly obstructed. According to NFPA 72 Section 17.6.3.313, if beams are greater than 18 inches and spaced more than 8 feet apart, each beam pocket shall have its own detector. This ensures no pocketed area is left unprotected, as heat may collect within each bay without spreading quickly to adjacent areas. Per NFPA 72 17.6.332, heat detectors can be mounted on the beam bottoms when beams are under 12 inches deep and spaced less than 8 feet apart center to center. The heat detector app in the NSVcad fire alarm module helps users design code-compliant detector layouts by calculating design spacing. It automatically adjusts for ceiling height and structural obstructions like beams and joists to ensure accurate placement. To begin, users should define the building structure and walls using the Define Structure app. In this demonstration, we will define the joists, assuming the other walls and construction elements are already specified. To run the app, click the icon or type NHD. The app interface will then appear, prompting you to select the unit of measurement for your layout, the applicable NFPA 72 edition, the system type, and the detector orientation. Next, input the listed spacing of the detector and ceiling height. Once you've entered all the necessary data, click the Insert Detector button to place the detector on your drawing. When the detector is positioned in an area with joist construction, the software automatically adjusts the spacing by 50% perpendicular to the joists. Additionally, the app ensures that the detector is placed directly beneath the joist to meet the requirements of Section 17.632 of the NFPA 72 code. In areas with beams, the software automatically reduces the spacing of spot-type heat detectors to 2/3 of the listed spacing perpendicular to the beam direction. For beams exceeding 18 inches in height and spaced over 8 feet apart, the app limits the detector's coverage area to each bay. In corridors with smooth ceilings and regular geometry, the software automatically adjusts the detector's coverage area to an optimal detection radius. Users can modify the coverage shape by pressing S for square or C for circle on their keyboard. Pressing the Control key opens a pop-up window that displays relevant information, including the required number of detectors based on either the circular or square layout shown in the drawing. The software intelligently analyzes room geometry and layout to optimize detectors fully aligned with the requirements of NFPA 72 and project specifications, ensuring reliable coverage, avoiding overlap, and reducing installation costs. I hope you find this video helpful. You can find more information from nsvsoft.net website.